Okay, this is a quick video on rates of change in calculus on overall expectation A1. So we kind of covered this in class today, which was Thursday, April the 12th. Okay, so this is just a video about calculating instantaneous rates of change using limits. So back in grade 9, we talked a lot about rate of change. So we would have a graph of a line, of a straight line, and we wanted to find the slope of it, or the rate of change. So we would select 2 points on the line and determine the rate of change by doing rise over run. So rise being the change in our y values divided by the change in our x values. Another way to say that would be we took this point here, found its y value, and found its x value. So it had a y and an x value. And then we took this point here and found its y value and its x value, and we subtracted them. So we determined this formula, rate of change, change in y over the change in x, to be y2 minus y1 over x2 minus x1. So it's just determining what's the change in the y's and what's the change in the x's, and then we divided it to get our rate of change. So that was great in grade 9 because our lines were straight and we could just pick 2 points on them and find the rise over the run. Now we run into a problem because we don't always have straight lines. Rarely do we. So if we look at a graph that looks like, say, this curve. Okay, well, the problem here is that the rate of change is constantly changing. So at every single point on this graph, there's a different rate of change. See, the rate of change here is pretty steep, and it's getting less steep, less steep, less steep. Eventually it's 0, and then it's going negative. So our rate of change is constantly changing on a curve. So we never worried about calculating the rate of change before. So in this class, we've already talked about calculating the average rate of change on a curve. So if we had a curve and we wanted to find the average rate of change, we could select 2 points, just like we did in grade 9, and draw this line, which we called the secant, which was helpful in determining the average rate of change. But now we're saying, well, we don't want the average rate of change. We want the instantaneous rate of change. So we want to look at a graph. So say this curve, and maybe we want to know what is the slope rate here at this point, at this x and y value. I want to know what is the slope. So in this case, we're interested in the slope of the tangent line. So we call this a tangent to the curve. So it's a line that just touches the curve at this one point. And the slope of it is what we're looking for. So that will tell us what the instantaneous rate of change is. Instantaneous rate of change at this one point. But we can't do rate of change with 1 point because we need to know 2 values. We need to do y2 minus y1 over x2 minus x1. So we run into a problem because we only have 1 point. Now we could select another point on the line, but we don't know what that line is. We don't have an equation for it. So we are going to use limits to help us kind of create 2 points on our curve that are really, really close together so that we're able to find the instantaneous rate of change. Okay, so let's try an example. So we've got a pebble. Which I've spelled peeble. Okay, we've got a pebble. Is that right? I don't know. We've got a stone. And we're going to throw it off a cliff. So let's just say this is our cliff, and here's the ground. So we've got this little stone. So we're going to throw it off off of a cliff that is 80 meters high. And it's going to follow the path of a parabola. It's going to take 4 seconds for it to fall. So it's going to start at 0 seconds, and it's going to take 4 seconds to fall. So that's our stone. And I'm telling you an equation for this relationship is S of t is equal to 80 minus 5t squared. So this equation tells us the path that the stone is going to take as it falls all the way to the ground. And it's going to hit the ground at 4 seconds. So I could also tell you the domain of this graph would include any values from 0 to 4. So when t is greater than or equal to 0 or less than or equal to 4, this graph is true. Because that's what's happening. And then it's stopping, and then it's landing on the ground. So that's our graph. So we're going to figure out how to find the slope at one point on this graph. So this is like our y-axis. This is our x-axis. This is like time. And this is height. We use function notation, so S of t just means what's our y value at time t, and t is like our x value. And so let's just say at 2 seconds, we were interested in learning what's the slope or what's the rate of change at that one point on the graph. So we want to know what is the slope just right there. It's also, the slope in this case is like distance over time, so it also is telling us how fast the stone is falling. It's the velocity of the stone. Okay, so what we're going to do is we're going to use limits to help us figure this out. So essentially we're doing y2 minus y1 over x2 minus x1 to find our rate of change. But we only have 1 point, 2. So before we start, let's figure out what our y value is at 2 seconds. So I'm just going to sub a 2 in for t. So 80 minus 5 times 2 squared, so it would be 4 times 5 is 20, 80 minus 20 is 60. So I know my y value right here is 60 at 2 seconds. Okay, cool. So I've got one set of points to work with, 2 and 60. But I need another point on my line to help me find the rate of change. But the problem is, I don't want it to be far away, because then I'll be just using the average rate of change between these 2 points, which is like a secant. But I don't want that. I want the slope of that at this one particular point. So this is going to be crazy. But we do this thing called, we take the limit as h approaches 0 of this equation. A plus h minus f of a all over h. Okay, so this equation, sometimes called the difference quotient, it's pretty much as if we're doing a secant, so as if we're picking 2 points and finding the rise over the run. But we're saying the distance between these 2 points, so we're saying this one's at 2, and then we're saying this other point is at some value 2 plus h. So we're saying this is a distance of h apart. And then using this limit thing, we're saying, well, we kind of want h to be 0, because if h was 0, they'd actually be the same point. But it's weird because we can't use the same point. So we're just talking about using a value that's really, really, really close to 2. So we're using like 2, and this blue guy could be 2.000000001. It's just something that's very close to 2. And then our y values are going to be, well, we know one of them is 60, and at our other point, it's going to be whatever f of 2 plus h is. So I don't know what that is, but instead of subbing in 2 for t, we'll be subbing in 2 plus h. So we've created this variable h that just is kind of like the x value difference between our 2 points. So you're going to see this formula come up a lot when we're trying to calculate the instantaneous rate of change, also known as the slope of a tangent. We're going to use this equation. So in this example, a is actually equal to 2 because we're trying to find the slope at t equals 2. Okay, so I write limit as h approaches 0 every time. I already knew f of a, I already knew f of 2 is equal to 60, or s of 2, I guess in this case it's an s. S of 2 is equal to 60 when the time is equal to 2. So then I want to do my h ones. So when my time is equal to 2 plus h, what's s of 2 plus h? So I'm getting my second y value. So my equation was 80 minus 5t squared. So I'm just going to sub in for t. I'm going to sub in a 2 plus h squared. And I can't obviously solve this for like an actual number because I don't know what h is, but I can simplify this expression. So I can go 80 minus 5. I can expand this bracket. 2 plus h squared actually means 2 plus h times 2 plus h. So I know that's going to equal 4 plus 4h plus h squared. So it's just like foiling this bracket. Then I'm going to multiply the whole bracket by negative 5. So I'd get negative 20 minus 20h minus 5h squared. And then I'm going to collect like terms. So 80 minus 20 is 60 minus 20h minus 5h squared. Okay, so that's my second y value. So essentially I'm just doing y2 minus y1. So y2 was 60 minus 20h minus 5h squared, and I'm subtracting it from my y2 point, which is 60. And the whole thing is over h. Or the whole thing is over x2 minus x1, but see what happens? x2 is 2 plus h minus x1 is 2. So the 2 minus 2 ends up canceling out. So you just have an h on the bottom. Okay, so then I'll just continue with this limit equation as h approaches 0. So you can see 60 minus 60 is going to end up canceling out. So we're just left with negative 20h minus 5h squared over h. Okay, now I notice that each term has an h in it. So I'm actually going to factor out an h from the top. Factor out an h, and I'm left with negative 20 minus 5h over h. So all I did was factor out one of the h's from each of these terms so that I'm able to cancel these out. So now I've got the limit as h approaches 0 of negative 20 minus 5h. So here we're at a standstill. Can't really go any farther simplifying. So now what I'm going to do is I'm just going to shove the 0 in for h because I want h to be as close to 0 as possible. So let's just throw in the 0 to see what our y value will equal. So now I can get rid of my limit thing because I'm actually subbing in 0 for h. So that goes away, so I'm left with negative 20. So it turns out this is my slope when time is equal to 2. So that just tells me my pebble that started off at 80 meters high and landed on the ground at 4. I know at 2 seconds, which is 60 on the graph, I know that the slope right at that point, the slope of this tangent line, would be equal to negative 20 meters per second. So that's how fast my stone is falling. Okay, so a little bit confusing, but it's how we use limits to estimate a rate of change at one point on our graph. We introduce this variable h that allows us to pick 2 points on the curve that are actually right over top of each other. Okay, we couldn't sub h in right away because that would have resulted with a denominator of 0, which we can't have. Okay, so hopefully that made sense.